Intelligent Transportation Systems Podcast. Welcome back and happy holidays to everyone. I'm Javier Sanchez Medina from the Intelligent Transportation Systems Society. Hey, here's one piece of advice. Listen to this intro I'm reading to the end of it. You'll understand why later. Well, we have prepared a special episode about two events coming from the Spanish chapter of the ITS Society. First, this chapter has organized a first ITS PhD and Master Degree Thesis Award. We got to interview a PhD Awardee Professor David Vazquez. His thesis title was Domain Adaptation of Virtual and Real Worlds for Pedestrian Detection. Are you into computer vision? Are you bored of labeling objects in real-world scenes? Well, these smart guys in Barcelona have a very nice idea using a virtual world to train that detectors. Additionally, this chapter has organized another talk within the IEEE ITS Society Distinguished Lecture Series. The chapter president, Professor Miguel Angel Sotelo from the University of Alcala, invited and introduced Professor Raul Rojas from the Free University of Berlin, in Germany. He came to talk about autonomous driving and his lab's recent challenging and exciting experiment. They sent their automated prototype for a 2,400 kilometers journey in Mexico. So we have some very interesting comments from Professor Rojas. Finally, we also have a new book comment from Professor Haluk Eren, this time about the book titled Vehicle Safety Communications, Protocols, Security and Privacy, written by Luca Del Grossi and Tao Zhang. Don't miss it. Let me now finish this opening cut with two very important announcements. First, we are very happy to announce that the ITS Society is just about launching the first issue of the Transactions on Intelligent Vehicles. If you want to receive this historical first issue, you need to hurry up. Please consider extending your IEEE Intelligent Transportation Systems Society membership to include the new journal in your member benefits. If you are not ITSS member yet, well, this is the perfect time for you to join us. We have at this issue post at ITSP.cicai.com the URL you need to use. The second announcement is a holidays announcement. We have a present for you, our selected and special listeners. Press pause after I say this. Go to your email editor and send us a message to ITSPodcast@gmail.com with the following text in its subject: I am an ITS podcast listener, I want my holidays gift. I repeat that. Write us an email at ITSPodcast@gmail.com with I am an ITS podcast listener, I want my holidays gift as the message subject. If you include in that email body your service address, we are sending you something you will like. But we only have 120 packages ready to be shipped, so you have to be quick. Press pause now and send us that email. I'll wait for it. Okay, are you back? Did you send it? Let's start now with the book comment. Thank you. Enjoy it.
This is the book review section for the present issue of ITSPodcast, reviewed by Dr. Haluk Eren, Fırat University, Elazığ, Turkey. The book title is Vehicle Safety Communications, Protocols, Security and Privacy, and consists of 396 pages, written by Luca Del Grossi and Tao Zhang. Authors are namely associated with Mercedes-Benz and Cisco Systems. The book was published by John Wiley and Sons in 2012. Specified chapters were written with the support of additional authors. Target readers of the present book are ITS researchers. Also, this book could be a useful resource for undergraduate students and engineers. The book combines state-of-the-art technologies in vehicular communication safety. This emerging field refers to safety, reliability, communications of connected vehicles, safe vehicular networks and systems. as reading the book, researchers and engineers may get most recent research information about this trend topic. The reader will also get clues about the overall system of safe communication between vehicles and infrastructure. It indicates fundamental viewpoints, design considerations, and protocols to ensure safe communications for vehicle to vehicle and vehicle to infrastructure. Besides, the book describes emerging challenges and their possible solutions to build up trust for inter-vehicles, secure data exchanges, and maintaining privacy in vehicular networks. The book discusses up-to-date major advancements of vehicle safety communications by stakeholders. Therefore, it presents a tangible resource for next-generation studies. This material provides a welcome position between underlying theory and implementation simplicity. The associated issues are embedded into many individual chapters, which are consistent with each other. Totally, 22 chapters exist in the book. The first 3 chapters are allocated to conventional automotive safety issues and their application areas. They address motivation, comprehension of the book, and background information for vehicle safety applications. Initial chapter exhibits road traffic statistics of fatality, injury, and property damage in United States, European Union, Japan, and the rest of the globe. Then authors discuss vehicular safety systems in historical perspective, specifically from the second half of 20th century and recent decade. Reader can find solid examples for active and passive safety systems, such as seatbelts and ADAS. Finally, vehicle safety components are presented, consisting of driver units, sensory systems, and inter-vehicle networks. It also explains multi-sensory vehicular data in terms of security. The chapters from 4 to 9 mention about wireless communications for vehicular safety. Firstly, the relevant issues of connected vehicles are introduced. Afterwards, vehicle communication modes, vehicle networks, and their application requirements are discussed. Existing technologies are evaluated in the sense of vehicle safety communications. Then, authors describe assigned frequency band for 5.9 GHz DSRC and the wireless access in vehicular environment standard protocol. Subsequent 2 chapters explain the physical and medium access control layer of IEEE 802.11p standard. Readers can find optimal data rate for DSRC and wave upper layer protocols, including the wave short message protocol and the IEEE 1609.4 standard for DSRC multi-channel operations. At the end of these chapters, safety applications are introduced, which are developed as part of recent collaborative efforts between academia and other parties. Chapters 10 and 11 deal with vehicle-to-infrastructure and vehicle-to-vehicle concept and their applications. The next chapter expresses DSRC scalability and congestion control algorithms for vehicle networks. Chapters 13 through 21 are devoted to security and privacy protection for vehicular networks. Authors initially describe security and privacy threats and requirements in a large-scale vehicle network. Then, they provide a cryptographic background of security and privacy in vehicles' communication networks. The following chapter explains public key infrastructures, consisting of digital certificates for large-scale vehicle networks, and talks about digital certificates and the PKI privacy preserving. Here the authors categorize privacy preserving digital certificate management in 3 groups, that are shared certificates, provisional certificates, and group certificates. A reader can find a brief comparison for them. Then the authors mention about protecting driver privacy against potential violations by appropriate security arrangements and its support systems. Finally, they talk about the IEEE 1609.2 standard underpinning security over DSRC networks. The last chapter of the book, Chapter 22, introduces the fourth-generation cellular networks to support vehicle safety communication applications. To add more about this book, it needs mid-level communications background. In addition to vehicular safety communication preliminaries, it promotes feature research in this significant domain. Some of the chapters are supported by simple mathematical principles, and many of the arguments are sketched by descriptive figures. Reader can find the references at the end of each chapter. As a final word, hope you enjoy when reading the book.
Hello again! It is now time to jump into our today's main courses, our interview with Professor David Vazquez and Professor Raul Rojas. We hope you enjoyed them. They are really illustrative, I promise. We are now with the winner of the Best PhD Dissertation Award that the Spanish chapter of the Intelligent Transportation Systems Society has granted to Dr. David Vazquez Bermúdez from Autonomous University of Barcelona. Hello, David. Can you please introduce yourself to our listeners?
Hi, Javier. Nice to meet you. My name is David Vazquez. I'm from the Autonomous University of Barcelona. I studied the degree of computer science here. Then I studied the master in computer vision and artificial intelligence. And then I started the PhD thesis with the Professor Antonio Lopez from the Advanced Driver Assistance Systems group, where I did my PhD thesis. Currently, I'm a postdoc in the Computer Vision Center and a professor in the Autonomous University of Barcelona, and I'm working together with Antonio Lopez in the development of an autonomous driving car.
Sounds like fun. Congratulations, Dr. Vazquez. Great job. Your PhD dissertation title was Domain Adaptation of Virtual and Real Worlds for Pedestrian Detection. Can you please summarize what was it all about?
Yeah, of course. I have been working in pedestrian detection. That is an important key in advanced driver assistance systems for the vehicles for preventing the collision of the vehicle with the pedestrian. These systems are based on classifiers. These classifiers are based on features and are trained on images. Images are very difficult to acquire because you have to take the car and go out and take a lot of images with a lot of good information and relevant information. And this data have to be annotated. The annotation is very difficult. It is very boring. You have to take manually and annotate where the pedestrians are. And also it is prone of error because it's a manual task. Then we started to think, how can we avoid this? Then what we give up is, what we realize is that we can use virtual worlds. We can use video games, and in video games you can automatically generate the scenarios, and you can record them and automatically get the ground truth. Then you don't need a manual annotation. Then we collected this data, training a pedestrian detector, and suddenly it worked well when you apply it in the real world. Then we tested with different scenarios, and we realized that it doesn't work as good as if you would train in the real world with real images. And this is because of the dataset shift. But this happens also when you have a system with a car, for instance, with a black and white camera in Spain, and you record some data and train your classifier. And then you go with a different car, with a color camera, for instance, in a different country, and then you test the model that you train in the other setup, and this doesn't perform as good as if you will train and test with the same setup. And this is called dataset shift. And there are some techniques called domain adaptation that allows one classifier that is trained in one domain to adapt to a new domain. Then in my thesis, we propose different techniques for doing this domain adaptation using active learning techniques, or one method that is called data augmentation or data mixing, and then we solve this problem. But of course, the domain adaptation methods that we propose are very basic. Then Yaolong Chu, that is a new student of Antonio, that he finished the thesis this year. He proposed new methods of domain adaptation. And currently in our group, Germán Ross is increasing this work, is augmenting this work, and not only for pedestrians, but for semantic segmentation. This is with the virtual world, we generate the sequences, and then the goal of the computer vision algorithm is to say for every pixel of the image which object it is. So it has to detect the road, the traffic signs, the sky, the buildings, and this annotation is much more difficult to do than annotate as a pedestrian, and we are doing this with our virtual world again and with domain adaptation.
So I understand that you're still working on pedestrian detection, right?
Yes.
Can you please tell our listeners what is the knowledge frontier in that area right now? What is the state of the art? Can you brief it?
Yeah, of course. There are a lot of pedestrian detection methods, and there are also systems in the cars that are already working. So the question is why to keep working on this. So the next step is that when you detect a pedestrian, sometimes it's very late. You detect the pedestrian, but you cannot avoid the collision. So the goal is to detect the pedestrian before. So what the community is trying to do now is what they call intention analysis. So you have to prevent, to see what the pedestrian is going to do. You have to go inside of the mind of the pedestrian, know if the pedestrian is going to cross the street or it is not going to cross the street, and then to take a decision before. And the other area of research is now the deep learning. Deep learning is creating a revolution in computer vision. So this is also happening in pedestrian detection. But there are a lot of work in this area because for object detection, the deep learning algorithms that there are currently, they are not very fast because deep learning started with image classification. So there are a lot of things to do in deep learning for object detection, pedestrian detection.
Mm-hmm. Okay, again, congratulations and our best wishes for your career after this sparkling launch. So thank you.
Thank you very much.
Bye. Hi there. Are you a usual listener of this show? Maybe you will like this. We are launching a YouTube channel where you will be able to subscribe to our show if you want. You can find the channel link in this issue post at ITSP.cicai.com. So help us by subscribing, liking, or sharing our episodes. Thanks. Let's now get back to our today's interview. My guest today is Professor Raul Rojas, a Mexican based in Germany since 1982. Professor Raul Rojas is the leader of the Autonomous Labs Center and also Professor of Artificial Intelligence at the Institute of Computer Science of the Free University of Berlin in Germany. He has such a reputation on the artificial neural networks field, but he is also a very reputed scientist in the field of autonomous vehicles. His team's latest great achievement has been the 2,400 kilometers autonomous journey that their prototype, called Made in Germany, has just accomplished in Mexico. Hello, Professor Rojas. Can you please introduce yourself to our listeners?
My name is Raul Rojas. I'm a professor of computer science at the Free University of Berlin. I have been there since 1997. And before that, I was a professor at another university in Germany, in Halle, and also in Vienna. I have been working on several different things like neural networks, robotics for soccer games, so the so-called RoboCup competition. We have been also building autonomous vehicles, but the main idea is to give artificial intelligence a body, and that's the kind of work I have been doing for the last few years.
We are in Madrid this time because this afternoon Professor Rojas is just about to deliver a distinguished lecture sponsored by the Spanish chapter of the IEEE Intelligent Transportation System Society about the famous project Made in Germany. Professor, can you please explain what is all of this about and how is it any different from other autonomous vehicle projects we're seeing, for example, in Germany, Italy, the United States, Spain, or many others?
Well, we started our project in 2006. At the time, there was a call for a robotic competition in California, which was held in 2007. And many of the teams working today on autonomous cars, they were present at the competition. For example, the people doing the Google car, they were at the competition, or people working with Delphi in the US from Carnegie Mellon, they were at the competition. People working for Volkswagen in Braunschweig in Germany, or people working together with Daimler-Benz in Karlsruhe and Stuttgart. They were all at the competition, so we're all. It's a small community. We were all there. We started more or less at the same time, and the objective is the same. So everybody wants to have a car which works like a taxi. So you just call the taxi, tell the taxi where you want to go, and then the taxi takes you there. And then you just step out of the car. The car continues servicing other people. You don't have to take care of the car. You don't have to park the car. The cars are working all the time. They are moving people in the city. So that I think the objective is the same for everybody. And there are different, for the commercial use of these vehicles, there are different objectives. For example, in the case of the automotive companies, they want to make ready the autopilot for the highway within the next few years. Other companies are more aggressive, like Google. They want to have autonomous cars in the city. But I think that the main ideas, the main techniques, they have been shared over the years, and everybody is doing kind of the same kind of work. And I think that the different projects are comparable maybe not in the scope and what they want to achieve within the next few years, but in the range of techniques that we are all using.
Mm-hmm. Can you please describe the sensors and technology used? The Velodyne on the top of that vehicle is quite obvious, but what other sensors are you using?
We are using a lot of sensors, and I always say that we don't really need so many sensors for driving an autonomous car, but our car is more like a laboratory on wheels. So we have laser scanners, we have radars, we have video cameras, 9 video cameras. We also have the rotating laser scanner on top. We have a very accurate GPS navigation system. So we have the full range of sensors that other projects are using. But having them all, you can switch on some sensors and switch off other sensors. For example, we can now locate in Berlin using only the video cameras. So we can switch off the laser scanners and then try to navigate using computer vision.
Using what, landmarks or?
Using landmarks in the streets, especially three-dimensional landmarks. The difference, for example, with Google is Google uses two-dimensional landmarks. They look at the floor and at the markings on the floor, and then they do a matching. We are trying to avoid two-dimensional markings. We also use them for centering the car on the lane, but we are trying to avoid them for localization because in Europe we have a problem they don't have in California, which is snow. So anytime it snows in Berlin, and it snows sometimes several weeks during the year, you cannot see any line on the street, and yet the car has to be able to locate itself. So that's why we are stressing three-dimensional features instead of two-dimensional features. The kind of techniques that you can use for that, for the localization and matching, is the same at the end. But I think that that's the only difference we have with the other teams, that everybody's trying to develop some kind of technique. For example, the people from Daimler-Benz, they are stressing computer vision. Google has never thought very highly about computer vision, so they use the laser scanners for object detection and even for looking at the white markings on the street. They use a laser scan and the reflection of the laser scanner. Now they are trying to do more computer vision. They also have a very good team now working on computer vision. So everybody works on different approaches, because once you have so many sensors, then you can try different things. And I think that's the interesting thing also from the different projects I have seen, that everybody's trying to do something else, and then you can complement what other people are doing. And commercially, at the end, maybe the cheapest techniques are the ones who are going to survive. My personal bet is that computer vision is going to be able to do autonomous navigation, complemented by some kind of GPS system plus radar. But we will see. So that will happen in the future.
Mm-hmm. Well, I've seen that in your lab you're using a not so common technology. I think you are investigating on controlling a vehicle with a set of brain sensors. Is that right? Is that kind of technology involved in this project?
Yeah, we did that because some of our projects have a more commercial objective, and we are also working together with companies in Germany. So we have been working, for example, with Volkswagen and BMW and other companies, where I have PhD students and they have special projects within the company trying to advance some of the techniques that we use. But we also do some kind of what I could say showcase projects, where you want to show how far the technology has come, so that you can do things that 10 or 15 or 20 years ago were unthinkable. One of our showcase projects was using EEG sensors, a brain-computer interface, put that on the head of some people. And then these persons had to learn to control a computer game with 4 directions. So they had to be able to move a sphere to the left, to the right, up and down. That's 4 directions. We can associate those 4 directions with movements of the vehicle, for the steering wheel going to the left, going to the right, or accelerating and braking. These are the 4 kind of states that we recognize. And then you can put a brain-computer interface on a student, and then let the student train the interface, and then drive on the streets, even on the streets. That's more a showcase, because we are not really trying to make people drive with their brains. We are trying to make computers drive for people, so that people can use their brains for other things. But from that project, what we did, once we showed that that's possible, then we transfer the technology to wheelchairs. And now, instead of driving cars, what we are driving are wheelchairs. And the people who have been using the wheelchair, they can drive inside buildings. They can also drive the wheelchair outside buildings. And the sensors on the wheelchair, which are also laser scanners and computer vision, they are there just to avoid accidents. So, for example, if you are driving the wheelchair with your brain, then it could be that the wheelchair comes out of the sidewalk. But that's prevented by the sensors. So the sensors don't allow you to get out of the sidewalk. So you have like a corridor where you can drive with your brain, and you don't have to be that concentrated, because the wheelchair is also taking care of your safety. You basically only have to control the wheelchair at the corners, where you think, I want to go to the right or I want to go to the left. And that was a kind of derivative of the project that we did with the car. But of course, the project with the car was the one who attracted the most attention, because it's a fascinating thing to be able to drive a car with your brain.
Okay. And this project has a leg in the connected vehicle mode, or is it just a standalone platform?
We are starting to work with connected vehicles, because now we have 3 cars. So we have three vehicles that we can put in autonomous mode. And now the big issue also for the future, for the next few years, is what do you want to do with car-to-car and car-to-infrastructure communication? So this is going to happen earlier than autonomous cars, because in the US they are already preparing the law for making sure that every new car sold starting 2018 has to have car-to-car and car-to-infrastructure communication. So every new car. So it's just a matter of waiting 10 years, and then more than 90% of the cars are going to have telecommunication. And then the question is, how do you use that for coordinating traffic? So what can you do? Once your car can communicate with other car, what do you want to tell the other car? So do you want to, for example, do you want to agree on a common speed on the highway? Or do you want to know if the car in front of you, 100 or 200 meters ahead of you, just did a full brake, and you get that communication, and you can be more careful when you are driving. So telecommunication is going to be used for coordination of cars driven by humans, but we could also use telecommunication for coordinating robotic cars. And then the ultimate goal would be to use telecommunication for coordinating cars driven by humans and robotic cars, which is a very difficult problem. How do you communicate with humans? What's the best user interface? What's the easiest way to pass information to humans so that they are not overwhelmed by the amount of information coming from everywhere? So it's a very interesting research topic, and we just started a project in Berlin in this direction within the framework of a big German project where about 12 or 13 groups are collaborating. And the point of this project is that how to do telecommunication between robotic cars and humans.
Mm-hmm. Great. Well, to finalize this short interview, Professor, can you share with our listeners what are the next challenge you are facing in your lab? Can you please share in what area of autonomous driving are you and your people working right now?
Yeah, well, one thing we are working on, I already mentioned, that's telecommunication and coordination. But one thing which we have seen across the years, which is going to be one of the main problems for having autonomous cars in cities, is understanding what people are doing. So when you are driving, you are all the time, you're not just keeping your lane and driving ahead. You're always watching the traffic, and then you know from watching the other cars if the car in front of you is going to cut your path, or if it's going to turn at the corner, even if they don't use the lights, the blinking lights. You kind of know from watching the behavior of other vehicles what they are going to do next. This is very easy for humans, very difficult for computers, because it's like an intuitive way of thinking for humans. And that's one of the main challenges, and everybody has that challenge. So we just had a conference 2 weeks ago in Germany between all the groups working on autonomous cars, and nobody has intention recognition. But everybody thinks it's going to be very important if you really want to be safe especially not just on the highway, especially in cities where you have to recognize the intentions of drivers. But more difficult than that is understanding the intentions of pedestrians. So pedestrians sometimes use hand gestures to tell you that you can go. They don't want to cross the zebra stripes, that you can go, or for other purposes. And we have to be able to understand what people want to do, what pedestrians want to do, or cyclists, which are also very difficult to handle in traffic. And that's, again, very, very easy for humans, very difficult for computers. So we are starting to work on that. And the third thing that we want also to understand is how do people drive when there are no markings anywhere. So that happened to us now in Mexico when we were driving. Sometimes we had the white lanes, and we knew we had 2 or 3 lanes. But sometimes we didn't have any kind of markings on the highway or on the street. So it's your choice if you want to drive in 2 lanes or 3 lanes, and you have to figure out how many lanes are being used here by watching the other cars and by trying to make some kind of assumptions. That's very difficult today. So everybody doing autonomous cars is using really the markings of the highway or the markings of the streets. But in the future, we should be able to drive without any kind of markings, just by creating the map on the fly, the map of the city on the fly, deciding what to do, like humans can do, but robots cannot.
Okay. Well, thank you very much, and thanks also for your participation in this event. Thank you.
Thank you for the invitation.
Okay, it is now time to wrap up this issue. Remember, reclaim your holidays gift. Extend your ITSS membership to receive the first transactions on IV we are publishing in January, and be ready for the launching of the YouTube channel of the ITS podcast also in January. These are the 3 messages we had for you today. Thanks. This podcast is sponsored by the IEEE Intelligent Transportation Systems Society, website designed and managed by the Innovation Center for the Information Society at the University of Las Palmas de Gran Canaria in Spain. Soundtrack developed by Rubicon, audio edition, post-production and dissemination by the Institute of Cybernetics at the University of Las Palmas de Gran Canaria. I'm Javier Sanchez Medina from the IEEE ITS Society. We'll be back soon bringing you again the cutting edge of science at the Intelligent Transportation Systems podcast. Thanks for listening and drive safe.